Assalamu alaikum. Hi, everyone. Welcome to our one-day free workshop for reservoir characterization and modeling. We will start by 5 minutes presentation about reservoir solutions. Then Mr. Tajuddin will start. So for Reservoir Solutions, it's a company specialized in providing technical studies and courses for oil and gas companies and professionals. The company incorporates many professionals with diverse technical background related to oil and gas exploration and production. Our services include technical reservoir studies, field development planning, reservoir static and dynamic modeling, economic feasibility studies, technical support for academic researches like PhD and master degrees. Also, we are assisting in writing technical papers and publishment. Also, we are providing technical petroleum courses by the industry experts. Also, we provide mentorship programs. Our next course, which will be in 23 on June, reservoir characterization using core analysis, routine core analysis, and special core analysis. It will be 1 week hands-on workshop. For the content of the course, the first day will be on the coring, how to prepare a program, how to decide the sidewall core or conventional coring. Then the day 2 will be for the measurements, analysis measurements like the fluid saturation, porosity, bulk volume, and permeability. Then we will talk about the rock typing methods like the FZ, Winland, and so on. Then in day 3, we will go to special core analysis. We will talk about the special core analysis measurements like wettability, the electrical properties, and the capillary pressure. Then we will talk about the saturation height modeling and how can we use the saturation height into the static model. And we will also talk about the relative permeability, how to normalize and the average relative permeability, and so on. Then in day 5, we will talk about the data or core analysis data processing for the reservoir modeling, how to represent the rock types into 3D model, how to populate the rock types into 3D models. We will have a practical, very 100% practical course that will initiate from 0 to hero. We will initiate from the raw data for the core analysis until populating the properties from the core analysis to 3D static model. For our webinar today, the instructor for our webinar today is Mr. Tajuddin. Mr. Tajuddin Pinesa is a results-oriented and accomplished professional with more than 15 years of experience in identifying the location, quantity, and quality of hydrocarbon. Proven track record of success in conducting uncertainty analysis, maximizing asset value, implementing technical assessment, and advising on field development plan optimization. He is expertise in directing offshore drilling operations, acquiring reservoir data, minimizing geological risks and uncertainty, and devising and executing 2-phi, 2-porosity, 2-permeability models. Demonstrated ability to update and maintain 7 ICG and 1 INA geomodels, analyze and integrate geological data, establish geologic frameworks, and build long-lasting relationships with staff. He is widely recognized as hands-on leader, strategic problem solver, noteworthy communicator, and skilled coach. Actually, Mr. Tajuddin has a broad experience he worked into Petronas and also in Libyan oil companies. For the agenda for our today webinar or workshop, we will have 3 lectures. The first lecture will be about the reservoir characterization and the modeling objectives, then static data integration and modeling. It will last about 45 minutes. Then we will have 10 minutes for questions. Then we will have 5 minutes for a break. Then we will go to the second lecture, which will be about the reservoir characterization workflow and the conceptual model. What is it? And the lecture will last about 45 minutes. Then we will have 10 minutes for question and 5 minutes as a break. Then we will go to the third lecture, which will be about the static modeling workflow and static dynamic iteration process. And the lecture will last about 55 minutes, and we will have 10 minutes also for questions, then 5 minutes to conclude all the information that we took through our workshop. For the webinar rules, when you have any question, you can ask it into the Zoom chat and our instructor will answer it into the suitable time. Mute your microphone and camera. In case that you want to have a certificate for attendance on that workshop, please fill in the form that will be sent into the Zoom chat. The certificate will be received through 1 week after the workshop. For our upcoming courses and webinars, you can join it through our webinar and YouTube. Also contact us through mail or WhatsApp. In case that you wanted to register to our upcoming course, you can register it from the links that will be sent into the Zoom chat. Thank you for all attendees, and Mr. Tajuddin, you can start.
Yes, thank you very much. I will share my screen now.
Okay.
Can everybody see my screen?
Yeah, you can start.
That's good. Okay. Okay. So today our topic is one of the most important topics in the not the oil industry only, but in every industry and in exploration or development for natural resources. Today we will talk about the RCM, which is the abbreviation for reservoir characterization and modeling. You know, when we go to the fields, when we were students in geology or reservoir engineers or geophysicists, we used to look to the nature. We used to look to the nature as the sky we see in this slide. So we think about how I can take this nature with all the complexity and the complicated processes inside and everything, and use it for myself. How I can change it into digital numbers that I can handle to make predictions and obtain good results that will be from which I would benefit in my industry. So simply, there are 3 steps that we that oil companies or the geoscience experts follow. First, to understand, you know, when you go to the outcrops or when you drill wells, so you obtain data from the rock. Okay, so you start first to understand this data, what they are telling you. So you are in the phase of gathering information before even start thinking about building a model or even characterize it. So you need to obtain informations to understand. When we go to the outcrops, we measure thickness and we take samples to examine and to take to the lab to measure the petrophysical properties. and everything. Then we go to the next step, which is the characterize. Okay, so I now I characterize my, or identify what what type of the rock that I have available in my hand. Is it limestone? Is it coal? Is it sandstone? What kind of structure? Is it anticline? Is it syncline? Is it fault? So I start creating a synthetic data that enable me to understand, or to characterize my reservoir. So that, so in this stage, I can draw what I can see. I see I see a fault structure, then I can draw it, I can sketch it with my hand. So because now I understand what this data tells me, so that I can characterize. So I use my free hand to characterize what I see. Then I will move now to the model, because I moved from the phase of characterization, where I could first make sketches or 1D, 2D figures for my for my reservoir, okay, or for the formation. I could and I could understand and make some measurements for some properties and numbers, such as the numbers for thickness and distribution and the extension of the rock units. Then now I get into the next stage, which is the model. Now I want to make a 3D model. I move from 1D 2D data into a 3D data, which will help me to exploit the resources and get the maximum revenue from exploitation. So now, let me introduce the presentation summary. First, we will go through the reservoir modeling definition. You know, in the modeling stage, what we do is that we are building a reservoir model. So what is reservoir? Reservoir modeling definition. We will go through the reservoir modeling definition and objectives, and get to know why reservoir modeling as such an essential and daily basis project for oil companies. Because now reservoir model is used for different projects, not only for volumes assessment and recovery. No, there are a lot of objectives to do reservoir modeling, such as studying the mechanical properties of the rock, even in EUR projects. In coal and methane projects. So there is a variable use applications for reservoir modeling. So we will go through the objectives. Then we will go to the objectives of your company. Why we will talk about this? Because the reservoir model represent the base or the solid floor on which field development projects are achieved. It represents essential key element through FDP or field development plan workflow to reach desired desired objectives or targets of the company. Then we will go to talk about the reservoir simulation and the difference between when we say the reservoir the difference between reservoir modeling or the reservoir model and geological model. Then we will go to one of the very important parameters is the mass for working in field development plan, or when we are working as part of the RCM, which is a teamwork. The teamwork is very essential, or the key element for accomplishing successful RCM study and FDP plans. Because mastermind is represented by teamwork. So any successful project would not reach the top and succeed without teamwork. So in this part, we will recognize the technical positions required to accomplish reliable reservoir modeling and tasks that that everyone must accomplish to generate valuable inputs into the project. Then we will talk about, as we said in the second part, the cellular model, which is the origin or the root of any model, either the dynamic model or the geological model. So we will define it. We will talk about the specificities. You know, each object has certain specificities to be valuable, to be so that we can apply it for our advantages. So geocellular models or the static models, they have a certain specificities that need to be followed and applied so that you can call the geocellular model a reliable to for RCM workflow or for accomplishing field development. Then we will, after that, we will understand the main differences between the geological and reservoir model, as both serve different objectives in different domains, but both serve or represent part of the RCM workflow. Then we will, as we said, we will talk about the specificity of the reliable cellular models. So first, what's reservoir model definition? Reservoir model is a grid of cells which allow us to manage very important two important things. First, the key heterogeneity. Yeah, you know, any reservoir in nature, it's rarely to find it homogeneous unless you have a good a nice or clean sand bodies like the rivers, like the braided stream, like the braided rivers. But this is not always the case. So if I just open the whiteboard, in nature, usually, if you have, for example, if you have a reservoir of nice shaped channel like this one, okay, and you have a well, you drilled several wells, so you have a well here and well here, okay, so you expect that since you are drilling in the same sand body, so you expect that you have almost a homogeneous reservoir, homogeneous in terms of facies, in terms of reservoir properties as well. But unfortunately, this is not always the case, because if you have a reservoir composed of different stacking bodies of sand with different depositional phases ranging from braided to meandering to point bars, and also so it's not always expected to have it homogeneous. So the reservoir model comes to we build reservoir models to highlight or to show us the heterogeneity or the key heterogeneities that affect the flow units from which the hydrocarbon is coming into the well bores. Also, the reservoir models represent the lithophases and petrophysical properties distribution consistency. As I mentioned here, if you have a homogeneous body of sand, you expect to have the same average porosity, for example. Okay, but in case let's say in carbonate, it's no way that you can find heterogeneity is always the address of carbonate. So when you talk about carbonate, you are talking about heterogeneity. So representing the models to represent the heterogeneity in carbonate reservoir, it's truly a challenge. It's truly a challenge, and it's not easy to find that. But you need to highlight the distribution and what the differences that this heterogeneity causes in terms of phases and in terms of petrophysical properties. Sometimes you have a sand also, but you have a different body of sand. So you have a channel goes like this, and you have another one crossing like this. You have a third one that goes like that. Okay, so you have a different set of bodies. I saw some of these in seismic, and it was very beautiful image, but dealing with this, dealing with heterogeneity, it was a nightmare. Okay, so going back to the presentation. So as I said, we do reservoir model for these to manage and represent these very important two elements, which is the heterogeneity and consistency of the data. So, what the reservoir model is for. The main objective of reservoir model actually is not to predict. Okay, there is a confusion about the notion of the reservoir model. Actually, it's not to predict what we should find in the reservoir. What we should find in the reservoir, it's not it's the first concern. It's the main target in the exploration phase. So when we are drilling a well, so let's say that there's a company drilled some wells somewhere. Okay, they found a discovery. They found from the seismic that there's a nice structure somewhere. Okay, so they have their field goes this way. Okay, and we have a nice structure. If you take cross section, let's say that we have a fall goes this way, and the company drilled the first exploration well. Actually, the exploration well enables us to find what's inside the reservoir. Is it oil, gas, or nothing? So what I want to say is that the main objective from reservoir model is not to predict what we should find the reservoir or else. It's to anticipate the dynamic behavior of the reservoir. We are going through a long process in RCM, okay, workflow, just to understand how this sand body or the rock body that we see here, when we put wells, how these wells will perform, how the reservoir will behave and produce the oil or the hydrocarbon from inside. This is why we build a reservoir model. So reservoir model is mainly used for to simulate field evolution through time. So we use it for anticipating or predicting well production, well behavior as well, fluid movements within the reservoir at certain time, and also pressure evolution with time. How the reservoir after drilling this exploration well, and we started developing our field by drilling a lot of development wells here and there and there and there. Okay, the model should tell us before we drill this development wells how the pressure will differentiate, or how it will change through time. This is what actually the most important objective for any reservoir model. So the geo reservoir model is one of the most not talk about reservoir model. I'm talking about geo model now. Now we are talking about the static model. Okay, the static model represents one of the most important phases in integrated reservoir study workflow. When we are talking about RCM, as we said earlier, we said understand, okay, characterize, and model. The model, it has two phases, as we will see later. The phase one is the static model or the geo model, okay, and the second one is the reservoir or the dynamic model. So what the geo model represent one of the most important phases in integrated reservoir study workflow. Why? Because it integrates multiple data from different disciplines, which include reservoir geometry, reservoir characteristics, petrophysical properties, phases, everything. So, okay. It also takes into account dynamic information. So as a geomodeler, when you are building a static model or geomodel, you take into consideration some dynamic information, such as the production data, which is presented by PLT. Also, you will consider the XPT, okay, that assist you to define that assist geoscientists to define the fluids contact. Also, the core data, the core analysis, porosity, and permeability, all these things should be integrated into the model. Also, it provides a key heterogeneity modeling. After all the data being gathered and integrated, it will enable us to make or build a robust model that reflect the heterogeneity inside our reservoir, based on which we can understand how the fluid will behave until certain point in from now until certain time in the future. So actually, in this part, the person who's needed in this part is actually the geologist or the geomodeler who's in charge of this part. Now let's come. We talked about the objective of reservoir modeling. The objective, actually, the objective reservoir modeling is part of the objective, or it's referred to the objective of the company. What the company want from from modeling the reservoir. When companies make new discoveries and they had all the information and data that enabled good understanding of the reservoir, it's now time to make the reservoir profitable, to make money, okay, as much as it can. So the new discovery fields start to be subjected to development projects by drilling more wells to improve production, hence actually increase the recovery. So through field life, companies tend to acquire more data on regular and planned time to monitor reservoir behavior and steer their direct or steer their reservoir toward the maximum profit target. So this is actually the objective of company. So they build the reservoir model, and they keep updating the reservoir model based on each target. Okay, so when we say that, and let's say that in 2000, let's say in 2002, the company made this discovery well, and in 2002, 2003, they drilled appraisal well. Okay, the appraisal well job was to check the boundary of the field, the extension of the oil water contact, and so on. Now they are happy. Now they make their first FDP. Okay, they make their first FDP, which is the field first development project. Okay, and they set number of they apply the RCM workflow. Okay, and based on this on the results, they decide how many wells they want to drill, and how much these wells will produce until from 2000, let's say from 2003 until, let's say, 2010. And after this time, companies may revisit the model and update the model using the data that has been obtained from 2003 with 2010, or which I mean here the new wells that the development wells that drilled. Okay, because from 2003 to 2010 there are several wells was drilled. This is a first well, second development well, third development well, fourth development wells, and so on. Okay, so all these wells will be integrated into the next FDP plan project, or the next static model, to update and enhance our understanding for the reservoir flow behavior. So to obtain the optimal profitability of project, there are key informations that we need to acquire. Okay, acknowledge, acquire, and most which is summarized that require the knowledge of three important factors. First one is the volume in place, okay, which is the hour stope, how much hydrocarbon are there under our feet. We have a field, okay, before we do anything, how much oil. And this is usually calculated, or primarily calculated, from the first 3 or 2 wells from the discovery or exploration wells, and the appraisal wells as well. Okay, so it gives us a probabilistic, it's not fixed volume, it's probabilistic volume, but at least we know how much initially under our feet, and also how much will be recovered. We're talking here about the reserves. Usually companies tend to make several scenarios based on reserves, on reservoir heterogeneity, pressure data, and also the data adequacy and reliability. There is a long process in the reservoir modeling part associated with the recoverable reserves, because there is always uncertainty. As we are drilling more wells and obtain more data, this uncertainty reduces, but it doesn't end. Uncertainty always remains. So always there's a probabilistic run to calculate the recoverable reserves in several scenarios. And also how the wells are expected to behave. Okay, how the daily production will be before I drill this development well. Okay, I'm planning to drill 4 or 5 wells. How much these wells will provide me from the total volume that from the total reserve that I will produce. So the expected well performance is another target, or the company need to be aware of before paying money for any FTP project, or to apply any RCM workflow. Okay, so now let's come to the integrated field development plan. Why they call it integrated field development plan? Because it integrates. It's a multidisciplinary integration. This means that integrate data from different resources, and also multiple members or expertise are from different disciplines are involved in this project. So it's a huge project. Okay. Objective of any development plan is simply to increase production. Okay, so the companies set, as we said in the as I mentioned earlier, that companies apply FTP projects at every period of time to increase the production, to exploit the reservoir to the maximum benefit. So any development project, okay, generally goes through essential four phases. Phase 1, which is the 3D geological model. Okay, 3D geological model, you input the geological data inside the model, petrophysical data, and you come up with the volume assessment. Okay, and the volume assessment can help the CEO or the CEO of the company to make business decisions about how we can exploit this reservoir or this field. Because if it's economical, then there will be decisions, business decisions, and if it's not economical, I don't think that it will be a good chance to decide business decision regarding any economical reservoir. This is for example. After that, once the geological model is done, it will be transferred to reservoir part for reservoir model or dynamic model to simulate flow, or to build flow simulation model. So based on the simulation model, okay, the company will be able to forecast, okay, or to predict the production. Because based on the prediction, company can set the expenditure for the development, which includes drilling new wells or and making data acquisition. So and also how much they will specify as expenditure for surface facilities, which includes the pipelines, the crude and gas storage, water treatment. All the surface facilities depend on how many wells will be drilled, and the distance between these wells, and also are they drilling, are they producers or they are injectors. Okay, as we said, integrated field development project, it's a multidisciplinary multidisciplinary workflow. You have several data from different resources, as we can see here in this table. Actually, it's a summary. The table that you see it takes more than 2 slides maybe, or three more slides, but I try to summarize it so that it can be simple to understand, because this is only the geological part that I'm showing here. So still there is a part for the reservoir engineer part, the geophysics part. So, as I said, any FTP project need data from different disciplines. These data go through variable processes, okay, so to provide solid interpretation for reservoir quality and also the behavior. It's a teamwork. So you have data such as seismic. You need data such as seismic. Seismic can be regional or taken from analog fields. You can also use the well logs and cores. What do you need this data for? For first, to construct the geological models, to build structure grade, stratigraphy grade, sedimentological, and also you need this data as well to, as we said at the beginning of the presentation, is to characterize. Okay, to build a concept. We will talk about the concept in the next slides, which is in the characterization phase. So this synthetic data, or the studies or results, okay, is carried out by experts from disciplines such as geophysicists, the geophysicist, and the geologists, petrophysicists, and reservoir engineers are in charge of carrying out, of integrating this data, not only obtaining the data and interpretation. No, it's integration. And also we have the well test data, fluid sampling, lab experiments, cores such as the CCL, which is the core analysis, the SCAL data, which is the special core analysis, all of this, and also taking fluid samples for PVT, for doing well test interpretation. All this data is integrated and interpreted by reservoir engineers, geophysicists, geologists, and petrophysicists, because, as I said, it's it's integration project, not only individual. Each one works separately. No, everybody should work together. So, what's you hear about reservoir simulation? So, what's reservoir simulation anyway? Reservoir simulation, it's the you can see that it represents the end, okay, the end product or the end stage of geological model. So once the reservoir, once the static model has been built, okay, so I have my static model. Okay, so once I have the static model built, with all the integrated studies inside, so I have the phases, okay, I have the porosity, I have the K, which is the permeability, I have fluid saturations inside it, inside all the cells, fluid saturation. I have the thickness, okay. I have type of the structure as well. Is it fault? Is it faulted? And so on. So once all these data are integrated into my static model, the static model will be transferred to reservoir to start building the dynamic model. Or let's say, why do we need dynamic model or the reservoir model to run simulation? We will come to this in more details later. So dynamic model or reservoir model. So what they first they input their dynamic data, okay, from production and pressure and so on. Then they run simulation. To predict the field behavior and see how much these wells can produce. I hope that it's understood. Okay, simulation is Simulation is a numerical process, okay, for dynamic input to produce production and injection history of the field. What's the outcome of all this long process? Is history match curve. History match curve for each dynamic parameter inside the reservoir, including the oil production, the gas oil ratio, the pressure, and so on. All this, the final target of the reservoir simulation is to provide a history match that can tell us whether this reservoir model is reliable or no. And that depends on the match degree between the input data and the output data. So as we said, for the dynamic models, okay, the main inputs, because most of the inputs are in the geological model, but in the dynamic models, okay, we need the production and production data or injection rates. If there's injection wells, we need the pressure, because pressure changes over time, so it's very important input into the simulation, and volumes of produced oil and water. So now we come to we come as one of the most important part of the workflow of RCM, which is the teamwork, okay, and working with your colleagues. As we said, that FDP and RCM workflow, it's a long process and it's a multidisciplinary. So you need different expertise from different disciplines, such as the log analyst. Log analyst is the is the one who carry out quantitative and qualitative log interpretation. Okay, he is the one who identify the fluid contacts from logs, from XPT, highlight essential petrophysical parameters for robust petrophysical model. So it's the output of log analyst is very important input into the reservoir model. There's also the lab petrophysicist here. Maybe we can call it the core specialist, who is the not the core specialist who is in charge of core acquisition. No, we are talking about the person who is doing or measuring petrophysical properties, especially porosity, permeability, and the special core analysis data in the core lab. So he's the one who provide the lab, let's call it lab-based petrophysical data through core and fluids analysis. Then we come to the geophysicist. Geophysicist is the, let's say that is the he's the one who's providing the boundaries of the reservoir. You cannot model the reservoir without knowing the boundaries of the reservoir, the top and the bottom. So geophysicist is the expert who provide seismic data, including but not limited to seismic horizons and faults and other attributes related to facies and fractures and all this data. So the inputs is very important and represent also the beginning of any workflow, as we will see a static modeling workflow, as we will see later in the next slides. Then another one who's the sedimentologist. Sedimentologist is the one who identifies sedimentary facies, the macro and the micro. It's very important to identify the facies, because the facies is the carriers of the physical properties. Each facies, but not always, have the certain characteristics. So they have a certain or special petrophysical properties that can be identified through facies distribution. So the sedimentologist can use the core description to identify the macrophages, use photography to identify microphages and porosity as well, permeability, and also can carry out correlation among wells to using core data to see or to tell us how the phases are distributed throughout the field. He also built a conceptual sedimentological model that showed the phase distribution, which is this model can be important input into the static or reservoir model. Then we come to the geochemist. Okay, he's a geologist who provide informations about the hydrocarbon fluids compositions and organic matters. And finally, we come to the reservoir engineer. Reservoir engineer is just actually his job starts once the geological input has been built and interpreted and built into a 3D static model. He or she will be in charge of sorry, I mean, maybe you ask where is the geologist in this in all this part. The geologist, he or she will be in charge of building the reservoir, the static reservoir model, by integrating all the data as we said earlier. Okay. So this slide summarizes the integration workflow for any RCM reservoir characterization and modeling project. So we have, as you can see, we have the geomodel in 3D. We have the orange bubbles, okay, which indicates the data that should be input into the geological model. We have the petrophysics from the core data. We have the sedimentological model that we talked about earlier, and that will be provided by the sedimentologist. Okay, fractures will be provided also by the geophysicist or also by the sedimentologist if we can spot these fractures from core. We have the log interpretation from the log analyst. Okay, we also have the reservoir attributes that is usually provided by the geophysicist. Reservoir attributes, or let's say seismic attributes, is associated with seismic data that can help us to that can help the geophysicist to detect any irregularities in the reservoir, so we can get attributes for structure, for fractures, and also for facies, and that also for sure depends on the quality of the seismic. We have also the then after that we move to the reservoir model. The reservoir model is the as we said, if you compare the number or the amount of data input, its reservoir model is not comparable to a geo model in terms of data, because as we said earlier, what we need is the protection and pressure data, and if there is and fluid characteristics for PVT into the reservoir model, while most, or let's say 70% of the data are input into the 3D static model. Okay, cellular models are we hear this. We always hear a static model, geological model, dynamic model, simulation models. So all these, the root of all these models is the cellular models. What's cellular models? It's a schematic description. A schematic description of not a reservoir, any object. So you are define it as the skeleton, okay, like the skeleton of a building. When you go to any, when you look to the buildings, I took some of these nice pictures for different buildings. The skeleton of these buildings it's not complete. It's just a skeleton. So these buildings later, it's like a reservoir, later will be filled with cement, will be filled with paintings and hardwares, furnitures, windows, and everything. So it's similar to reservoir. So first, we what we do, we represent our reservoir as a cellular grid or as a cellular model. Okay, contain a lot of cells that will be later filled or in which there will be the data will be integrated and input. So why do we need the cellular model? Uh, to understand the complexity of reality, you know, at the beginning of the session, we said how we can convert or how we can transform nature, um, uh, how we can change the complex. Okay, how we can change complex things to a simple that can help us to predict and make good results for our profit. So to understand the complexity of reality, okay, the relationship between inputs, the heterogeneity and frameworks, and also to quantify reality, which here we are talking about the volumes as we and reservoir properties, because we are not because there are several volumes used by the cellular. We use from applying the cellular from using the cellular models, such as the not only the hydrocarbon volumes, even the rock volumes, pore volumes, and all these volumes are essential outputs from any reservoir model or geocellular model. So this is two slides. I'm sure that you are familiar with the Gulfix. Gulfix, it's a North Sea field. I'm showing here two pictures for one for the geological model, okay, or let's call the geocellular model or reservoir model or dynamic model. So we have here an example for the geocellular model for porosity, okay, distribution. You can see that the reservoir before modeling has been divided, and we will see later in the workflow of the modeling how we create these cells. And these cells is filled with the input, okay, from the porosity input, and after that, how this and how this in the reservoir model there will be also the cells filled with production data and pressure data, but sorry, I don't have this is actually for I didn't put a picture for simulation grid. This is for faces. I was supposed to define it here as faces, so sorry, it's what it's a mistake. So this is a grid for porosity, and this is a grid for faces. And we will see later how we can create these cells or build a cellular model at the beginning of the static modeling workflow. So this is another example for cellular models. So you have cells distributed in 3D, okay, X in the X and Y and the Z direction. Now we will maybe you can have a break now, or we still have a time.
No problem, inshallah. If you wanted to have a break, no problem, inshallah.
Okay, but let's give first 10 minutes to answer questions, okay?
Okay, no problem, inshallah. So
Okay.
attendance, if anyone has any question, please put into the Zoom chat. Participants that were asking about the certificate, I will send the link for certification in after the second lecture, inshallah. Okay, and a certificate for the participation and attendance. Okay, so it's a time for questions. So if anyone that has any question, please put it into the Zoom chat.
Any questions, Guy?
Okay. Okay, so I think that we have some questions. We have 3 questions into the Zoom chat.
Okay. Plain, what kind of type you... Okay, I will answer this question in the second part when we reach the end of the static modeling workflow. Okay, Rando. Yeah, because here you are concerned about the uncertainty. So I will answer this question at the end of the part 2 when we are concluding with the when we reach the final stage of the static model. This is where we will handle the uncertainty and talk about the sensitivity for reservoir parameters. Okay, actually the thickness, the thickness. Okay, for Osman, the thickness of one cell. Actually, it depends. It's agreement usually between the geologist, and it's a subject of agreement between geologist and reservoir engineer. Why? In geology, we tend to capture the nature as it is. Okay. For example, let me explain on the explain in the whiteboard. In geology, we would like the model to be fine grid. Okay, what does mean fine grid? We need a grid that capture. We need a grid that capture. Okay, let's say that we have. I have this well here. Okay, sorry. I have this well. Okay, and I have let's say facies. Okay, this is facies. I don't want to go into much details, but this is a shale layer. Okay, and this is another facies. Okay, so we have facies 1 here. Okay, this is facies 1. Okay, and facies 2. This is shale, and this is facies 3. Okay, what we prefer as a geologist, when I build a static model, I need a cell size that capture all the faces that I see. So this means that I want cell, okay, to capture faces 1. Okay, so because I need a cell that represent these faces in reality. Then I want another cell, okay, that capture faces 2, and also another one, okay, that capture, it will be smaller, maybe it will be smaller than these 2 cells, okay, to capture the shale layer, because it's very important. Shale represent flow barrier, okay, in simulation, so it's very important to be captured. And also another one to capture faces 3. Okay, now we are talking in terms of geology, but when it comes to simulation, things is different. Reservoir engineers always prefer the coarse grid. Why? And they got the point, because when it comes to the flow, okay, the flow of hydrocarbon, okay, into the borehole is not. It's not. It's more pressure and permeability. Okay, it depends more on pressure and permeability than on phases. I'm not saying that phase is not controlling. No, it controls, but the production and the permeability, or this, let's say the field permeability, or larger scale permeability, or pressure permeability of buildup, depends control the flow of this hydrocarbon. So what they prefer is that they prefer a coarse, a coarse grid which contain a larger, okay, a larger cell, okay, that can represent the flow of hydrocarbon into the reservoir. The coarse grid, the problem of the coarse grid with the geology is that sometimes it skips the fine the fine intervals such as shell. Okay, because sometimes it cannot capture it. So we have a large cell for F1, large cell for F1, large cell for F2 or maybe F3, even if sometimes the heterogeneity, the coarse grid, the problem with the coarse grid that it doesn't capture heterogeneity. With the fine grid that geologists built, okay, it capture the heterogeneity, but the coarse grid, which is required for simulation, it doesn't capture it. So let me say that in for the geologist, the finer the grid, okay, let's say the cell size can be average can be from can be 2 or 1 foot, okay, and sometimes the maximum reach 3 feet. But for coarse grid, okay, which is preferred simulation, sometimes average can be 6 or maybe sometimes 9. That depends on the behavior of the reservoir. So this is this is how we can, as I told you, it's agreement. The thickness of the cell is agreement between the reservoir engineer and geologist. None of them can control the thickness, or let's say the average thickness, by the way, because cells they don't have the same thickness. All the cellular grid doesn't have the same. All the cells have a variable thickness, and as I told you, that is controlled by the heterogeneity and also by the behavior of the production. So reservoir engineer and geologist need to sit together and agree on average cell size or cell thickness. Yeah, okay, okay, host. Okay, I will talk. We will talk about how we can determine the context. Yes, sure. Yes. No, there's no difference for both, but there's no difference. Actually, the dynamic model is the same static model, but with dynamic input inside. Okay, so you have the static model, okay, with all the properties inside, the porosity and permeability, phases, and everything. And after you finish, you give it to the simulator or the reservoir engineer. What reservoir engineer? He takes the production data and pressure data and fluid data and put it inside the static model that you provided, so it becomes a reservoir model or dynamic model. Then he will run, or she will run the simulation and check the history match, and based on that, as we said, and based on the history match results, they will conclude whether the static model is reliable or it cannot be used, or it needs a modification for next phase for development. So there's no difference in dimension in cells, since it's the same cells. There's no difference. It's the same cells. The geo model provide to the reservoir engineer. Reservoir engineer just put the dynamic input inside. Okay. Sometimes in advanced stages, they deal with what they called partition. So, sometimes to test the because you are dealing with uncertainty. Subsurface is always uncertainty. However, how much data you get, it doesn't change the rule. You always have uncertainty. So they tend sometimes to do a partition. So they come to the cells like this cell, for example. Okay, and do some certain partition just to manipulate, or let's say not to manipulate, to tune the pressure along in the well, along around the well, and see the impact of the uncertainty on the flow or the production of the well.
Okay, Mr. Tajuddin, let's have the break, 10 minutes break, then go back.
Okay, 10 minutes. Okay. Thank you.
Thank you. Thank you.
Okay, I'm back. Okay, I will continue. Okay.
Okay, Mr. Tajuddin, you can start it now.
Okay. So as we said, when I encounter when I want to change, okay, I want to simplify things, okay, and change complex to simple. What do? I divide it into chunks, okay, into chunks of tasks. So so before initiating a cellular model, we need to apply this principle. Okay, I have a reservoir. Okay, what's inside this reservoir? It has a structure, it has a properties, it has beds of different thickness and different phases, maybe one or two, or maybe variable positional environments, thickness and extension, and everything. So before that, we need to divide, okay, or change, or from complex to simple. We need to divide the components of the reservoir into individual parts, okay, and why we do that? First, to understand each component in terms of quantity and quality, and secondly, to build a general concept about each part. So the first and the most important thing to do before even building a model, you need to divide the components of the reservoir. Why? To understand it. Okay, so you go to the first component. For example, here we have the first component is the reservoir shape and volume. How is the external envelope shape of the structure? The anticline, is it shape of the structure is anticline? Is it fault? Is it salt dome? The topography, topography or the relief reflected by the type of the contour for both top and the base of the reservoir. This is usually provided by the geophysicist. So you need to, before, as a geomodeler, before you get into this into the model, you need to, with the rest of the team, you need to understand each component separately, so that you can understand, or you can make a proper interpretation, and based on this interpretation you can start building your model. You cannot build a model just because you cannot build a model for any object just because you are looking at it without understanding what's inside, what's inside, the characteristics of the object. You cannot model it, otherwise the work would be rubbish. uh, uh, do we have a complex structure with many faults that divide the reservoir into compartments? And also the second component is the internal organization. The internal organization means that such as the correlation, uh, uh, the internal organization is how the elements inside are related to each others in a sightful manner, such as the Digafag architecture. We said that can be identified by correlation when we put the wells. Also correlation well by well, well to well, and also wells to outcrop. Sometimes you can correlate the wells to outcrop if there is a nearby for exposure for the reservoir nearby the field. Also faces variation in different trends, lateral and vertical, and their association with petrophysics. Also the presence of diagenesis structure, so, microstructure related elements such as drains and barriers. So all this, this is another component that you need to understand and build, to use it to build a concept for for your reservoir before initiating the model. So we are still in the characterization phase that we talked about earlier in the at the beginning of the presentation. We are still in the characterization phase. Second, you have the structure, also the structure framework for framework, which include the faults, fractures, as we microfractures. It's another worth quantifying. It's very important component. The last component is the fluid in place. So it includes the type of fluids, type and number of contacts. Sometimes you don't have you don't have one contact. Sometimes you have compartments. If you have compartments, this means that you expect to have different contacts. This is encountered in heavily faulted reservoirs. And maybe in and also in some basins like Sarawak, where you have a different carbonate reservoir cones, and each one has a different contact depth, pressure, also pressure and temperature of the reservoir, fluids composition, aquifer extension, energy, aquifer energy, and boundary, and everything. So you see, all in the as I said, to understand object, you need to the complex object. You need to divide the components into chunks, and you start studying each one separately to come up with understanding. So what makes the cellular model, okay, reliable? You will hear this word a lot during in your, I'm sure that you hear it a lot in your work, the word reliable. So let's start with the geological model. A geological model must be robust, as it takes into account the static data, such as the faults, the stratigraphic stratigraphic layers, the barriers, in case you have a multiple reservoirs, how much output data is representative. It can be the degree of representation of this model, all control the robustness or the reliability of the geological model. For reliable reservoir models, in which is, as we said earlier, it's the geological model with dynamic data input. It's strongly constrained by the geological model and dynamic data. And also understanding all understanding all this data, and to make and to be able, and this reservoir model should be able to make fluid flow simulation that can end up with a proper or let's say less uncertainty history match that can be later judge, okay, whether this model can continue, okay, to forecast and economical evaluation or no. Okay, now let's come to distinguish between the geological model and reservoir model in terms of data input and type of grid. As I said, answering a question asked before the break about the grid size. The grid is controlled by the cell size, actually. So let's go to the geological model. It's a static model, so it includes all the static data associated with the rock, okay, in the first degree. It also prefers to be a fine grid, okay, which is with a small scale, okay, X and Y, okay, for and Z for the for the cell. Then the reservoir or the dynamic model is it contains all the data associated with the fluids, like pressure and production and so on, and the grid size is always preferred to be coarse. Okay, this is an example for fine grid. Okay, this is for the fine grid for geological model. okay, which is used for volume calculation. So what are the puts inside? We put in each cell we put the phases, the porosity, effective porosity, total porosity, permeability, water saturation, gas saturation, and net thickness or net to gross thickness. So all these cells will be filled with geological and petrophysical data through upscaling processes, okay, and mathematical algorithms using different softwares such as Petrel, which is the most famous modeling platform in the industry now. So, the number. Another thing, control the the. Okay, we'll talk about this in the simulation stage. But as we said that in the static model part, on geological modeling part, is the grid or the cell size is always preferred to be fine. Okay, why? To capture heterogeneity. Now let's come to the reservoir model or the dynamic model, which is used for fluid flow simulation. So the same inputs, okay, will be there for geology, in addition to the scale data, including the relative permeability and capillary pressure, also the saturation, and also hydrocarbon saturation, and also the pressure data. Okay, and as we said, that it's preferred to be a coarse grid, so the cell size, the bigger dimensions, okay, the bigger X and Y and Z, so it's the better for flexible simulation flow. And also there's another constraint, okay, for a successful fluid flow simulation is the number of cells. Number of cells actually affect the simulation process itself. Okay, so it's always preferred that the simulation will be run in a decent time. Okay, in a time adequate to end up with good results without errors. Usually. The reservoirs that I encountered in my career, the cell number should not exceed 1 million, 1 million or maybe less. It's preferred. Yeah, can you believe that when you have a large reservoir, sometimes in the static model you create, the fine grid can have more than 3 million cells. But when you but when you move from the static model to the dynamic model, the reservoir engineer do upscaling process. Upscaling process. What does mean upscaling process? Is that enlarging the thickness, the thickness or the size of the cell, so that they can facilitate the simulation of the flow. So the number you expected to be reduced by more than 50%. But this is how it works. Simulation is better in coarse grid, and that's why dynamic model or reservoir model is always preferred to be the grid can preferred also always to be a coarse grid. Okay, let me move now to the second session, which is modeling workflow. Sorry, I'm trying to bring it to the screen. Next slide, just a minute. Just a minute, I have to stop sharing, okay? Okay, can you see my screen?
Yes, Mr. Tajli, yes.
Okay. Okay, now we come to reservoir characterization and characterization workflow. I intended to put this slide again just to remind us of the steps, how we can model the complex things in nature, or how we can model nature. We said that we need just to simplify to understand nature. So by dividing it, okay, into to understand it, characterize it by dividing it into components, okay, study it, interpret it, make a interpretation, then we take this interpretation, all the information and the synthetic data that we have got with the input, and put it into a model and build a reliable static model. Just to mention, at the beginning of my career, I passed through a very important lesson. I want to pass it to you now, guys. When I first started building the first model, I rushed into the taking the data and putting the model and building, and I was happy building the model and everything. But after I finished, my supervisor came to me, who was in my position now. Recently, I'm a development geology coordinator. He was the previous development geology coordinator. He checked my model for 5 minutes maybe, and he said there's a problem with the data because things is not consistent. So I realized, okay, that data represent 50% of successful static model. So because so data generally, okay, not and most importantly, must be reviewed and quality controlled. Okay, why? Because and this is your job as a geomodeler. Okay, when you are a geomodeler, you need to take care of this point. It's very important. When you find irregularities in the data, you don't proceed with the modeling. You have to stop. Okay, uh, data come from several resources. Okay, as we mentioned earlier, you have a data from provided by geophysicists, which is seismic data. You have data coming from petrophysicists. You have data from core. You have data from sedimentologists. You have a basin of input data that you need to pay attention before initiating or starting building the model, because if there's any irregularities, okay, you will end up with a model that doesn't represent the nature. So then it cannot be used for simulation to predict the fluid behavior. So the objective of data review, okay, is to decide if the data quality is sufficient to conduct a study. Sometimes like an exploration phase. Okay, let's suppose that the company drilled one well and they find good oil, okay, and they could from the seismic, a good seismic showed them that they have a large reservoir, okay, that have a boundary from from certain limit, but they still don't have enough data to start building or run RCM workflow. So what they need to do in this case, they will need to drill appraisal wells, what they call appraisal wells, to obtain more data, and they choose these locations based based on different target to serve different targets. It's appraisal wells that will not produce just appraisals, so they will have to take data, and that depends on the size and the thickness of the reservoir. So they need adequate data to start the RCM workflow and to build a model. Otherwise, the model will be very full of high uncertainty that will create a sense of high risk for the company to develop this field. And also, data review also enable us to plan data acquisition, okay, for the study purpose. Let's say that you want to drill a development wells, okay, so you are you finished drilling the first phase of development. The company finished was for 10 years. In these 10 years they drilled, let's say, 5 or 6 wells, okay. They check the data of these wells, were they adequate, were they adequate for the next phase of development, because the next development now, or the next FDP, they want to drill, let's say, another 6 or 7 wells, okay. Do they need to take new data or more data from these wells? And this is this is a decision, okay, for data acquisition. This is very important. I've been through this process in my career, and it's very important. You need to judge, review the data, and make sure if it's adequate, okay, or no. Is it complete? Is it validated? Is it is there a problem with the data? And based on that, you plan a data, you set a data acquisition which will be part of the FDP or the next FDP. So please underline this 2 words: data review or
Mr. Tajuddin. Mr. Tajuddin.
hello,
Yes, here.
hello.
Yes, you can start.
Okay, you can see my screen.
Not yet.
Okay, let me share it again. Okay, can you see it?
Yeah. You can start now.
Okay, do you want me to start from the beginning, or okay, I'll start from the beginning. Okay, so that
Okay.
everybody can
Okay.
catch. Okay. Okay, so as we said, as we mentioned in the first session, that that we need to follow 3 steps to model the nature or to change or to model complex things. The first one is to understand, okay, so to gather information, chunk the components, divide the components into chunks or or isolated, so to study it, which will enable you to characterize the reservoir and build a concept. Then you start building your static model. I wanted to I want to talk about the importance of data review. I don't know if you sorry for the sound cut. I want to talk about the data review. Data represent the most important part of the whole work of RCM. Okay, RCM workflow. You need to review the data. Either you are the geomodeler who is doing the job, either you are or you are petrophysicist in charge of the petrophysical data, or the geophysicist who is in charge of seismic data. It's the job not only for the geomodeler, it's the job of everybody. So data review is very important. Is very important because it comes from several resources of information. It's not so you have a data coming from the petrophysicist, you have data coming from geophysicist, you have data from reservoir engineer, you have data from all the resources. I'm talking here as a geomodeler. So as a geomodeler, you need to mine this point. So you need before modeling, make sure that your data is quality controlled and it's consistent. The objective of data review is to decide if the data quality is sufficient to conduct the study, because sometimes the data you have let's say that you have you drilled an exploration well in a large field, in a large discovered newly discovered field, okay, but the data is not sufficient. How much data do you have? You have data from only one well, and maybe it's not validated. Maybe the seismic is not is not clear. Maybe it's poor seismic data. So the data review will enable you to decide whether you want to drill more wells, okay, to obtain data, or you start initiating the development plan. But usually in discovered fields, they tend, especially the large ones, they tend to drill what they call it appraisal wells, okay, the job of these appraisals was usually to obtain more data so that the company can understand collect enough information to understand the reservoir. And also, the objective of data review is to plan to set a data acquisition plan for the study purpose. Let's say that a company made a field development plan and they drilled 5 wells for 10 to produce for 10 years. After 10 years, the company will do another field development plan by drilling 9 wells. Okay, so as a geologist, okay, in charge of the geomodel, how do you think that the data, okay, do you think that the data of the previous FDP wells were enough? Okay, is enough and it can be helpful for the next FDP project. If it's not enough, or maybe it's not good quality control, then you will set a plan for data acquisition for the 9 wells that will be drilled in the second phase in the second phase of field development plan. Because data acquisition, I've been through this process in my career, and it's a very important process. Data is always 50% of the whole project. Once data is validated and QC'd, then make sure that your project will be successful and it will go without with less uncertainty and minimum errors. But if data is not quality controlled, and not reviewed, then expect errors and problems, and static model will not, you will end up with static model that is not representing the nature, or not representing the actual reservoir that you are studying. So please underline the word data review or data quality control, because it's very important. So this is what you see here is the data quality control diagram, okay, or process, okay, that should be followed by the geomodeler. Okay, any geomodeler who's working on before initiating, when you upload your data, okay, you are uploading data from several resources, as we said, into your model. Before you do anything, anything, you need to follow or go through all these processes, check the completeness. Okay, for example, do we have a log that covering all the reservoir or not? Consistency, do we have a consistency? Do we have consistency between core data and well log data, for example? Accuracy, is the is there if you have you are sure that you have faces of shale and gamma ray is not exceeding, let's say, 50 or 60% in front of shale intervals, then here it will raise suspicions about the validity or the accuracy of this data. The integrity, are you able to integrate the data? Are you able to correlate porosity with permeability? And all these the processes you need to go through before initiating the model, and make even a report about this data, if they are usable or valid for modeling the reservoir on geological and reservoir level. So this is the workflow summary. We come to the characterization workflow. In this stage now, after we, as we said, after we we understood the components. Okay, we understood the components of the reservoir. Okay, we are now able to build a conceptual model. Okay, conceptual model is the model. The conceptual model can be sketched by hand. You can sketch it by hand for from the cinematological, from the structural data, okay, from stratigraphic data, lithological data. Okay, conceptual model is represent the base, okay, or the floor, okay, from which you start doing your work, because you cannot build something that you cannot imagine. Okay, so to build a structure model, you need to have an idea about the structure model, how many faults, the trend of the faults, like Sirte Basin. Okay, or we don't want to talk about Sirte as a basin, but let's say some reservoirs which has the same trend like Sirte Basin. Okay, all the faults in Sirte Basin, all the reservoirs, all the faulted reservoirs in Sirte Basin are most of them, not all of them, having the same trend, which is northwest southeast. Okay, so we need to put this into the concept model, so that we can apply it or involve it in the structure model. Do we have also, you need to build a conceptual model for the lithology distribution. Sometimes you have a heterogeneity, so sometimes you have a shaly sandstone in the point bars area, then you have a clean sand in the bottom of the channel. After that, you have a silt and clay in the flooding plain, and so on. So you need to have a I'm sure that some of you, or maybe all of you, saw the geologists who work on sedimentology, for example, how they keep sketching, drawing the depositional environment distribution in 2D. So this is because what he's trying to do is trying to build a concept model, so that he can provide it in his report for the company, so that the geomodeler can build static model matching the concept. So you are making concept, and then you build model that match the concept, which is you think that's what the reality is below or in the subsurface, with some degree of uncertainty, because you know it's subsurface. There's no 100% exactly right, so there's always uncertainty. After that, you come to the modeling workflow, and we talked about earlier. First is the static model or the geocellular model, then which is in which we will put all the static data and the reservoir characteristics from thickness, structural features, porosity, permeability, phases, and everything. Then a reservoir model where we will run simulation and see the flow behavior. Just example, just to show the comparison between homogeneous and heterogeneous. Homogeneous is like water. Okay, so it's a liquid has a certain uh, chemical and physical properties. Okay, so it's some reservoirs like clean sandstone reservoirs, they can be considered as a homogeneous reservoirs, as we explained at in the previous session when we talked about the channel. Okay, for braided system, for example, you expect to find parts or all the reservoir as homogeneous, where we have similar reservoir characteristics or reservoir properties. But unfortunately, in nature, it's not always the case. It's not always you find life is easy. Okay, especially with the heterogeneous sandstone and carbonate in general, because carbonate cannot be homogeneous by any means. So in heterogeneous reservoirs, static modeling will be more challenging, okay, than the homogeneous reservoirs. It will take longer time. Okay, there will be a higher degree of uncertainty, and that depends actually on, as we said, on data validity and quantity. Now, before these are examples for the conceptual model that we will have about each component of the reservoir. So before you initiating the model, you need to have a structure conceptual model. Okay, in your mind you have a concept model, how my structure model is built. Okay, for example, if I have do I have I need to have a conceptual model that shows my structure model goes like this. For example, if I go to cross section, okay, I have a fault. Okay, I have a fault. How this I have a fault this way. Okay, do I have fault? How this fault are trending? Okay, are they going in the same trend? This is a cross section. Okay, how many faults? Also, the number of faults is very important to highlight. Okay, the contact as well. The depth of the oil water contact. If are there fractures? Are they following the same trend? If I make let me this is a cross section. If I go to the plane view, okay, so this is my structure anticline. This is my faults. They are trending northwest. Okay, are they all trending northwest? Some of them, are they trending in different direction? Do we have fractures? Okay, do we have fracture corridors or fractures swarms or fracture associated with sterolite? There are fractures can be attributed to different physical processes. Do we have different sets? Do we have a compartment? Is my reservoir is one compartment, or there is a major or there is a major fault that divide my reservoir into two compartments? So this is a compartment and this is another compartment. So all this should be put inside the model so that it can be representative in terms of structure. So this is what you need to have. For a stratigraphic model is the same. Stratigraphic model you will use it to show the reservoir. You will use it to identify the reservoir layering based on the information that you have. So let's say how many beds do you have, how many beds, the thickness of these beds. Okay, because thickness of the beds is very important to define the grid cells. Okay, and also to determine the modeling parameters. You have also the sedimentological model, as we said earlier. The sedimentologist, after going through core description, doing petrography, see the collect samples and see the thin section under see thin section under microscope, to see the microfaces, to see the type of porosity, identify the type of porosity, see it for 2 or 3 wells. Then he comes with a sedimentological model that first that will define what's the depositional environment that I have. Is it a carbonate platform? Is it a fluvial system? What is it? What is it exactly? Is it patchy reef? Is it a bank? All this, is it a shallow? Is it a shallow? Is it a shallow tidal flat? So all this. All this information will be provided by sedimentological model, and again, the sedimentological model that you let's say the static model should have cells, okay, that reflect exactly the conceptual sedimentological model that the sedimentologist provided. Same for fracture, and same also for diagenesis. Diagenesis is a key point in carbonate, and it's and unfortunately it causes a lot of heterogeneity that makes that keep uncertainty level always high in carbonate, especially those who are passing, especially those reservoirs who pass through complex diagenetic processes and through burial time. Then it comes to the also the heterogeneity. If you have heterogeneity, you drilling sedimentologists usually encounter shale intervals, or let's say high K, or let's say call it hyper drains associated with sequence boundaries where we have a super K. So they call super K or super permeability, which is a very high. These intervals or barriers, or the high K intervals, should be identified and input into the model as per the conceptual is made. Then comes the fluid model, which is the oil water contact and or gas oil contact. Sometimes you have a complex structure, as we said. Sometimes you have a complex structure associated with the compartmentalization, which is associated with the faulting or major faulting in the field. So you are dividing, so it's dividing a reservoir into compartments. And this time you expect to have a different fluid contact, and this is what you have to understand, okay, how these fluids are distributed, their extension. Then you input that into your static model. So now, why we are modeling in 3D? Why do we make reservoir in 3D model? There are several benefits, okay, for this. First is the 3D is 3 dimension. We are building a model that represents nature in 3 dimensions, so in X and Y and Z. Okay, also 3D model can help us to understand or define the heterogeneity distribution, and also the connectivity associated with the barriers. Also, the best thing also what I like about the 3D model is that they are representing a huge database. Okay, so you have a database. Imagine that you have a database that have data from different resources, and it's quality controlled and healthy, and everything is fine. So it's a shortcut for you to use this data, to take this data and use it for another studies or another projects. because 3D model is like a filter, okay, for data. So so it keeps only the robust and healthy and quality controlled data, and doesn't include the error or bad or non-valid data. Also, static models or 3D models, they have a data resulted from the integration. So when we do data integration, we are creating a synthetic data, okay, which is the data generated from associating data with each other, like the core and Peter and will logs together, like the like the like doing some certain processes like a cutoff and some statistical equations applied on some data that from which you generated another data which is considered as synthetic data, and this synthetic data is used for modeling for modeling a certain reservoir property or certain reservoir characteristic. And also, and the most important, another one which is important is the volume. So we are using 3D to calculate the volume, not in well scale, no, in the field scale. And also the reservoirs or the 3D model enable us to run, okay, or do uncertainty analysis, okay, on each parameter of the reservoir in field in field scale in 3 dimensions, X and Y and Z. Okay, can we have time for questions?
Yeah, sure, sir. So attendance, yes, sir. Okay.
Okay.
Any of the attendees have any question related to the second lecture?
Sorry, I can't see the questions in the previous. It seems that it has been lost since the because of the cut that happened earlier.
Yes, yeah, okay.
But I remember there's a question about the uncertainty, and this is what I will answer in the next slide, actually, because we will go to uncertainty later after the volumes. So this is the only question I remember. So if anybody has a question, please type it. What are this is a good question. Okay, what are the QC part? Okay, in upscaling of the data. Okay, when we all right, let me bring the whiteboard. For GeoModeler, okay, I think I mentioned that earlier, but I will say it again so it can be clearer. Okay, so let's say that I have a porosity log. Okay, let me put this well. Okay, this is my borehole. Okay, and this is my porosity. Okay, from minus to plus. Okay, I draw my porosity now, so I have my reservoir here. Okay, in this part. Okay, then this the porosity reduces somewhere below, okay, and it comes back again high. Okay, so what I have reservoir, I have reservoir in this interval. So this is my reservoir. So I can say that this is my reservoir. Now, when you take the porosity log and you do the upscale, okay, or the scale up inside the 3D model, you need to run the upscale, okay, upscale to capture the heterogeneity, okay, and the behavior, or let's be more specific, the exact behavior of the porosity log. What does it mean? You mean you need to put cells in this way. how the upscaling process is done is like this. Let me just finish putting all the cells down here. Sorry, my drawing is not that perfect, but I'm trying to make things clear for everybody. Okay, so how upscaling process is happening? Let's take Petrel for example. Petrel, when you tell Petrel to run the upscale to porosity, it comes in this part. Okay, let's to this cell and see the equivalent curve of porosity. Okay, and see the maximum and the minimum value. Okay, and take the average. It calculates the average and it comes to put the value of average, okay, inside the cell. Okay, and he do the next step, he does the same. So he comes to the curve of porosity along this cell, okay, and take the maximum. Okay, this is the maximum. Okay, maybe this is the minimum. Okay, and calculate the average, put the average inside this cell, and keep doing the same all the way down. What's the quality control in this case is that all the cells after finish, they should have, okay, almost they should have almost identical behavior as the original log, because this is the input and this is the output. So I should have my my upscaled porosity going like this. Okay, so for example, this is the average. Let's say this is average. I can see that there's increase in porosity downward. Okay, so this means that I should have here average 10% porosity. Okay, here 15%. Okay, okay, and here it's much lower, so I say it's 5%. Okay, and this is increasing, so I expect to have let's say 18% or 20%. Okay, so you end up with a grid. Okay, you end up with a grid, okay, that matches the input data. If it's not matching the input data, then there's a problem. So you need to scale up the cells again and make them smaller. And that's why I say again that fine grid is preferred to capture heterogeneity. If you are, you can try it in Petrel or any other software, RMS, or even in Excel sheet, by the way. So the smaller the cell size, okay, the better capturing for reservoir heterogeneity and porosity and other properties behavior. So you have a cells, okay, which has a values that following the same trend of the input data. So you have here average porosity 10% in the input data. The cell has 10% average. Here you have a 15% average. Then this you have a 15% inside the cells. Otherwise, it's not capturing. If it's not capturing, you need to scale up again and put smaller divisions for the cells. So the output curve of, if you are taking the output should be like this. Okay, so this is the cell of 10%. Okay, now, and this is then we have the cell. Then you have a cell of 15%. Okay, goes like this. Sorry, I will choose another one. Whichever one is not helpful. So we said this is the cell of 10%. Okay, then comes the cell. Oh, I'm looking for a drawing. I cannot draw. Where's the drawing? Where's the drawing? Okay, this is the cell of 10%. Okay, and after that, you have the cell of 15%. Okay, then we come back to the cell of 5%. Then come back to cell of 18%, and so on. This is how it goes. This is how you control. So the cells, you see the trend of the cells, it should match exactly the input input data. Okay, don't expect the value to be exactly the same, but at least the trend. So you have here increase in porosity. The cells should show increase in porosity. If there's a reduce one cell or two, they should indicate the reduction in porosity. Okay. Is this presentation will be shared? I think will be. I think it will be shared. Okay, what's the approach used for selecting layers and zonation of the reservoir? Okay, that depends on the heterogeneity. If you have, as I said, if you have, as I said, your cells must represent the nature, must represent each component inside your reservoir, each phases. If you have a barriers, okay, or if you have hydraulic flows, or you have a super K or a super K intervals associated with sequence boundaries, then you can choose any approach. You can divide in the softwares like Petrel. There are several scenarios to divide the to apply layer and zonation, but you can choose any one of them. But that depends on the type. That depends actually on the type of the reservoir, and as I told you, the heterogeneity. Yes, you mean you can calculate without property? I don't understand. Can calculate directly from static model the all volume and place. This is the ultimate target for any static model, is to calculate volume and place. But if you are talking indirectly, okay, indirectly, you can do it by you can do it by going back to old school. Just calculate the area, average thickness of the reservoir, and you have the average water saturation, average water, and average net to gross. Then you have formation volume factor. You can calculate it, but it will be a roughly estimate. But static model with by doing the applying the full workflow of the static model by using by applying the full workflow, you will end up with volume in place more accurate. Okay, reservoir engineers for upscaling. Okay, there's upscaling process that the reservoir engineer do after the end of the static model. As I told you, they don't prefer the fine grid. they like the coarse grid. So there's a process in modeling softwares like Petrel, where you can take the whole grid with the whole properties, okay, and you start dividing the using multipliers. So you are taking the cells, okay, and you start multiplying using multipliers. So you take to convert the fine cells, okay, into larger scales. For example, 1 foot cells to 3 or 4 or maybe 5 cells. But that's actually it will impact the representation of the reservoir, and that will cause uncertainty to be high. You see, it's always this is very important. This is very important issue between static model and dynamic model, because both of them, they prefer different grids. But so reservoir engineer they do upscaling for the grid and change it from fine to grid, so you have larger cells, so that simulation can be in shorter time, and the flow simulation can be also smooth, okay, without any problems, without any errors. But actually this is not good for the static model, because it's no longer representing for it doesn't it's no longer representing the nature or the geological concept that we have built for the reservoir. Actually, it can be done by both, either it can be done by both, by the geologist or by the reservoir engineer. But most of the time, reservoir engineer do that because he's the one who has the pressure data and the all the dynamic data associated with the flow and like PVT and pressure. All this data can help him to judge or decide the upscaling parameters that he will put into the dynamic model. Most of the time we use stochastic. Deterministic usually deterministic can be applied for for homogeneous model, but for heterogeneous always we use stochastic approaches. Okay. There are several processes for stochastic because it's a subsurface. Okay. And each time you are drilling a well, you end up with a new data, and this data somehow shows deviation from the data from other wells which is adjacent, and this is called heterogeneity. And heterogeneity, it means that there's uncertainty, so the uncertainty cannot be handled using the deterministic model. Okay, so what you need is the stochastic. Okay, so what we are doing in modeling, we are model each parameter, each component, which is the phases, and there are stochastic algorithms used for distributing phases, stochastic algorithms for continuous data such as the porosity and permeability. For and also for water saturation. So okay, deterministic. Some deterministic models can be built, okay, in deterministic manner using empirical equations such as the SHF, which is saturation height function. Uh, um, yes, this is one of the famous examples that you can consider it or build it as a deterministic model. But most of the time, especially in carbonate, always we are using stochastic, and you don't run the stochastic process one time for one parameter for one reservoir property. You do running maybe tens or hundreds of times to take in consideration the probabilistic estimation of volumes. This is within the uncertainty that we will talk about later. Okay, SHF, you mean SHF? Yes, it's part of the static model actually. Okay, saturation function. You've been through different papers talking about how you quality control the saturation height function, but the easiest way for me, okay, for me is that you can quality control it by comparing with the PLT data. Okay, this is the easiest for me because sometimes SW logs or water saturation logs doesn't especially if you have a microporosity or you have non-connected vugs that cause you a lot of problems with water estimation or water saturation calculation to generate water saturation log. So it will not be reliable, or it will be invalid to use it for calculating hydrocarbon saturation. So instead we use saturation height function, okay, to build water saturation model. As I told you, to quality control, it's better to compare it with the BLTs to see if there's a consistency or no. This is part of the QC. Okay, can we have no more questions? Okay, can we have a 10 minutes break?
Okay, okay.
Okay. Okay, shall we resume? Hello? Okay. Okay, fine. I think everybody's fine. Okay. All right. Now let's come to static or geological modeling workflow. Okay, I took this workflow from Betrayal because it's the best. It's the best illustrative workflow that you can follow. Okay, and understand. It's very flexible and easy. So we start from the first thing, which is the data. Okay, we are here. In this part, you put data and edit. Data input as all available data must be, as we said previously, that must be QC'd um, and validated before uploading to modeling softwares such as Betrayal and or RMS or any other software. After that, GeoModeler, okay, take the seismic data, which include seismic surfaces that represent the stratigraphic boundaries of reservoir from top and bottom. Such seismic data such as horizons and faults used to build the structure model, which is the first step or the first brick in 3D static model. Because when you want to model a reservoir, you need the ceiling and the bottom, and this is what the geophysicist will provide you, is the seismic horizon and the top and bottom of the reservoir. Then you after building the structure model, okay, we built our structure model. Okay, so we have we have what we have. Okay, this is our structure. Okay, we have our faults. Okay, our faults placed in we did structure model that include also fault models. Okay, now what we will do, we will build the cellular model. Now we will build the skeleton. Okay, the skeleton grid. Okay, in which later properties and faces to be filled inside. Okay, so what do we do is that we are building a grid that will have cells goes like this, as we saw in different examples earlier. So you have cells all the way that should represent, and during building the grid, we need to mind the trend of the faults, because you cannot the trend of the grid should follow the trend of the faults, especially if the faults they have a certain trend or standard trend, northwest southeast or east west or north south. Also, you need to mind this when you build the skeleton, or the cellular model. Okay, then after building the skeleton, in Betrayal, it's known as pillar gridding. The process is called pillar gridding. I will show you some examples later. Next is the stratigraphic modeling. Here they mentioned that depth converging, okay, for the seismic horizons, but I'm showing the picture just to show you the make horizons process. In this process, we generate or we build the stratigraphic model, and how we can and the only one tool or the data that help us to identify the extension of the beds or the layers is the well correlation. When we correlate well to well, we can generate layers in 2D, then we convert it into 3D, as you can see here. Okay, after that, now what I have the structure model. My fault is there, the grid is there, the skeleton is there, filled with the static architecture is there. Now we will start processing of cell filling. We will fill now the fascias inside the cells. Okay, there's important note to note to tell you that the geomodeling softwares are dealing with discrete data and continuous data. Okay, discrete data is like fascias. It's like fascias. It has not a continuity in depth. Okay, so you have 3-4 feet fascias one, then half feet fascias two, then again, or maybe 5-6 feet. There's a gap. Another, then another 4-3 feet fascias four, and so on. So this is considered as discrete log data. Continuous log data is like the wireline logs, like the petrophysical logs, like porosity, like water saturation, all the data which have a continuous curve, continuous curve in this way. Okay, called considered as continuous log data. You will encounter these terms during your work, so you need to mind it. So this is called continuous data. While fascias, it have templates like this. Okay, so this is fascias one, for example, another fascias two. Okay, this is called a discrete data. Okay, so each template has a certain rock unit with a certain character. Okay, so this is fascias one, fascias two, fascias four. So this is called discrete data, and this is called continuous data. Just to know the difference between both when you guys start working in geomodeling in geomodeling work. Okay, so fascias modeling or data depends mainly on the availability of core data in the first place. If core data are not available, then fascias modeling cannot be accomplished, or things will be more complicated for geomodeler to represent the rock units inside the reservoir. However, fascias data is important. Actually, it's important to understand the heterogeneity and study connectivity. It's also support for reservoir property distribution in 3D, because what makes fascias different, okay, not only the characteristics in terms of thickness and in terms of pattern, in terms of relation to the adjacent up and down faces. No, also each faces has a distinguished or unique petrophysical properties. So to understand the distribution of petrophysical properties, we need to understand the distribution of fascias. So fascias, it's important. Let's say that we have built this is a picture for Gulfix fascias model, where you can see the channel with the leaves with leaves fascias on the side, the yellow color. After that, after finishing the facies model and you are happy with the facies modeling, then you come to the petrophysical to do the petrophysical modeling. This includes all reservoir properties. So you have a grid for porosity, you have a grid for permeability, another grid for net to gross, another one for water saturation or fluid saturation. There are different resources for petrophysical data that can be used in the model, from lab data to field data, which I mean here the wireline data. Now we come to the QC. Okay, this is can be done by plotting. Okay, by plotting the making cross sections. Okay, making cross sections like we do. Like we do in the geomodeling softwares. So what do you do in this case? Let's say, for example, you want to QC the structure, so you make a cross section to see the faults distribution. Are they identical to the concept that seismic provided you? Is the displacement, is it identical? The trend, is it similar to the concept that you have? The facies distribution, do we have are the facies are following the same trend? That uh, are they occupying certain not occupying uh, are they representing the same percentage in reality? Let's say that for example, reef facies, according to the sedimentologist, he says that it occupies around 20% of the total facies of the field. Is it the same in the model? Are they 20% or more or less? So all these things you need to consider when you are before proceeding to the volume calculation. You need to make review and quality control for the outputs, for the faces, for the properties, for the structure, for everything. You can do the quality control, by the way, after each phase. And this is preferred, by the way. You can it's preferred to do the quality control on plotting the data after each phase, after structure, after grading, after stratigraphic, after facies, and after petrophysical modeling, before you come to the volume calculation. Do not come to this step. Okay, do not come to the volume calculation, okay, without controlling the data and make sure that that your model is representing the reality. Okay, it should represent the reality. Make sure that your the average reservoir properties is similar to the model, similar to the from the model to what you have in the concept, or what you have according to your calculations. If there's a difference or deviation, do not get into this step, okay, until you make sure 100% that your reservoir or the model is identical to reality. Okay, then you come to the volume calculation, which is the final step. Here you assess the hydrocarbon volume in place, the rock, also not only the hydrocarbon volume in place, also the rock bulk volume, the net volume, as well as the pore volume. By finalizing this step, the model will be prepared to be transferred to reservoir. Okay, reservoir, to start work to add the dynamic data and input into the model and run simulation to see whether this model can successfully predict fluid behavior, and can be used, so it can be used to forecast production and field behavior in the future. And of course, the well design, it's actually at the after the step of the dynamic part. So we usually we design wells as per the based on the simulation results. Okay, so the simulation tells us that there are some certain areas where we have, let's say that the simulation indicated that there is some certain fee parts of the fields. Okay, let's say that we are in development phase 3. Okay, and there are some spots of oil. Okay, here we have a spot of oil or pool. Let's say pool. Okay, and there's another one pool here. Okay, here we have a degraded. Okay, we have a degraded oil. Okay, so it's consumed, cannot be produced anymore. Okay, And this is another one where we have, so what so the simulation shows us that there is a good pool of oil in this part of the field. So we make so the development plan will be based on 3 or 4 or certain number of wells to be drilled in this pool to produce. And at this in this part, the geomodeler will make a design or design wells. Okay, actually, it depends on the type of the well. Is it a trajectory or pilot hole, or is it horizontal, etc. So this is very summary for the workflow. Of course, the dynamic part, it has another it has another workflow prior to the well design. Sometimes you can make you can do well design just to identify the volume at certain places of the field, but it's not always the case. As I said, depends on the type of the type of the structure, if there's a compartments or no, if there's a heterogeneity, and so on. Okay, pay attention to this rule. You will hear it a lot in your job. So garbage in equal to garbage out. What does it mean? It means that we come back to the data. If you have a data valid and good and everything is fine, so once you are build a static model, the simulation will be run and the results will be optimistic and good, and the model will be reliable to build to go for predicting fluid behavior and develop the field. Once your data didn't go by the process that you have shown at the beginning regarding data quality control and validity, then you will end up with a rubbish model that will mean nothing for the project. So please pay attention to this to this rule. Okay, I'm showing you here. I'm showing you here some examples for structure model from the Gulfix example. It's available on the net. You can just type Gulfix model and you will get a lot of pictures. So this is an example for the structure model. Okay, where we have a seismic horizon, which is a top of upper Cretaceous. Then we have the fault model. Okay, this is how we model the reservoir. Then we have the skeleton, okay, or the cellular grid. Okay, usually like the buildings, okay, you don't have one roof of one surface of skeleton. You will have a multiple, okay, to support the weight. Okay, and this is in the normal building. You build several floors with several skeletons to support the weight of the building. But in reservoirs, we always have three only layers: one at the top, one in the middle, and one at the bottom. So, and this is you needed to represent the fluid. You may ask why we need the three, because you need to have cells, okay, all the way from the top to the bottom of the reservoir, so that you can simulate the flow and represent the reservoir properties. And this is a stratigraphic flow for the same field. So this is what we have. This is the input data that we get. So we do our correlation. We identify where are the channels, where are the leaves. Okay, so you have you have a concept about the distribution. So you have a sequence boundary here. You can see that all the layers are disappearing at this well. So it means that you have a sequence boundary. So you take this in consideration when you want to model the when you want to model when you want to build this model the stratigraphic architecture. So this is a picture for the 3D model for stratigraphic architecture. Now we come to the faces. I have shown you this in the beautiful picture for the meandering system. Okay, so this is nature. We want to transfer it into a 3D model using the core data. Okay, with the help of core data. and use and we quality control this data. We input into the model and we run, and we can see that we have a good representation for the channels where we have this. Where we have the channels in orange, and sided by the levy, which is the poor reservoir, which is the poor reservoir property, poor reservoir, or let's say the levy is the fishes which has finer sand grains like silt and clay, so there's no way to be a good reservoir, but it can be a good seeding potential. Did we come to the properties model? There's a missing picture here. Sorry, there's a missing picture here. Let me just erase it. Okay, that's it. Okay, we come to a property model. For property model, porosity, permeability, and water saturation, net to gross, what we use, the most important data is the core analysis. We need there are two types of core analysis carried out to model a reservoir to be to be more robust and reliable and more representative to petrophysical properties, hence can be used to predict flow behavior. First one is conventional core analysis, what they summarize abbreviated as a CCL. Okay, so we have the porosity, okay, of core, permeability of core, we have the grain density and the bulk density. All the four are input into the static model, in addition to reservoir characteristics such as thickness and as well as phases. So these are the most important for core analysis that we need to input into the static model to build reliable reservoir properties model. You know, porosity is the first property, and it's the most important property that we from which, or based on which, the other properties will be built, like permeability and water saturation. So it's very important to be quality controlled and to make sure that there's no problem with it. And there are it's considered as continuous data, so it can be distributed in 3D using several algorithms, but the most famous one is sequential Gaussian simulation, which is the famous one used for distributing porosity. Then we have the special core analysis. Unfortunately, special core analysis is not always obtained like conventional core analysis. Actually, it depends on the type of the well that will be drilled. It also depends on the heterogeneity of the reservoir and the target of the well. So what we have the relative permeability. Okay, we have the capillary pressure and waterability. For capillary pressure, it's the data that can be capillary pressure, which is the difference. It can be the difference in capillary pressure or capillary medium between the wetting fluid and non-wetting fluid, between the rock and the fluid. Usually, it's very important data to for this in the static model. It's very important because it can help to identify the transition zone. So when you have a capillary pressure data, so let's say what we have. This is y-axis and this is x-axis. Okay, I have here the water saturation. Okay, and here I have the pressure, and this is my curve. This is identical reservoir, or good reservoir curve. Sorry, it's not that perfect drawing, but I'm trying to make things clear. Okay, so what's the benefit from the capillary pressure? First, we can use it to model water saturation, and by creating SHF or saturation height function, by using saturation height function and create saturation height model that we talked about earlier. It also can help us to identify the transition zone. Okay, a transition zone for it. It can be measured from the point where we have irreducible water saturation. It means that no more water can be expelled out of the sample. Okay, so this is my irreducible water saturation. Irreducible water saturation. Okay, and the point from which what saturation start to decrease from here. So this is my transition zone. So it can help to identify transition zone so that we can put it into the model as well before providing to simulation. So actually the curve behavior is the different from sample to another. For example, in very perfect reservoirs, you will find this curve move inside. In sandstone, sometimes even the transition zone you cannot find it, or sometimes it will be very minimum. But in poor reservoirs, the curve will extend outside like this. And so I saw some curves in carbonate goes like this. So it's somewhat, and the and the average water saturation was 90%, and permeability was very bad. So it wasn't a good representation for. It was taken from poor reservoir property. So whenever the capillary pressure curves moves inward, it will indicate better reservoir properties. Outward, it will indicate bad reservoir properties. So there's no need to so there's no need to model it because it will be 100% or near 100% water. Now come to the KFI integration, or let's say one of the most important integration process between porosity and permeability. Once we have got the porosity model, okay, we want to model permeability, okay, and how to do that? How we can model permeability? Until now, okay, in carbonate, I'm talking about in carbonate, still there is a problem with the calculating or generating permeability logs for carbonate. There is always some degree of uncertainty that cannot enable the geomodeler to be sure that this data can help to build a reliable permeability model. So until now, what we do in carbonate, we do integration process between porosity core and permeability core, okay, and we make a plot. Usually, okay, if we have a relationship between porosity and permeability, then we can indicate it by a linear regression, okay, or the linear relationship, as you can see here, okay. From this curve, we can see that the more the change in porosity is followed by a change in permeability. So I can see that there's a good relationship between both. Since there's a good relationship between both, I can model the permeability, okay, based on the porosity value, and this is better. And this is better for me. And we, believe me, we tested this on some models, and we found out that this way is better than depending on permeability logs, where you will have some degree of uncertainty. It can be maximum at some intervals of the reservoir. So always in carbonate, so far use this method. So this is the experimental correlation, okay, that you will input into the model, okay. You will put into the model. So you have the log K, which is permeability, because permeability in log scale, okay, and you have the A, which is the slope of the curve, okay, and we have the porosity value or the porosity grid that you have built, plus the intersect value, which is taken also from the curve. Okay, Excel can help you so much with that. Okay, just a minute. Huh? Okay, so yes, so this is the plot, or the famous plot that used in the heterogeneous in heterogeneous reservoirs to predict permeability and model. Okay, now this is an example for Gulfix. Okay, we have some pictures here for Gulfix. So we have a porosity model. We have porosity grid. We have a permeability cellular grid. We have net to gross. Okay, net to gross grid, and we have finally water saturation. Water saturation grid. Earlier, someone asked me about I just remembered now that someone asked about how we identify the oil-water contact. Actually, there are two ways. Okay, the petrophysicist can identify the oil-water contact. Okay, which the old school. Okay, which is the well log interpretation. So we have and resistivity logs, and or water saturation, either from resistivity. Okay, or from water saturation log, or and the most accurate one. Okay, the most accurate one is what we call it the pressure gradient, which is indicated by XPT, which is a tool. Okay, XPT is a tool that measure or measure the fluid's pressure at different intervals along the borehole. Okay, so we end up, okay, as you know, in the borehole, what do we have? We have two fluids. Okay, in standard we have two fluids, or three fluids: gas, oil, and water. Okay, so when this tool XPT takes the measure the values of pressure at some intervals for the fluid. Okay, and this is the depth, or maybe, oh sorry, this is it's vice versa. This is the depth. Okay, this is MD. Okay, the measure depth, and this is the pressure. So when we plot the values of the fluid of the fluid different fluid pressure, we will find a change in the trend. Okay, when you find a change, or what we do is that when you find different in the trend, let's say that this is a measurement for interval with water. Okay, and there's a change in the gradient. This is a certain gradient for the part of the reservoir where there is water. Okay, for example, then we have we have a change in the gradient. Okay, it becomes something like this. Okay, so at this interval, okay, so this is the oil and this is water. So what the petrophysicists do, actually it's or reservoir engineer. Okay, he comes exactly at the change in the behavior. Okay, at the point where we have a change in the trend of the gradient. Okay, and take this as the contact between oil and water. And this is, believe me, the most accurate way, better than depending on the resistivity and water saturation, because as I told, because you know, SW is calculated from resistivity. Okay, and resistivity depends is affected by borehole conditions and reservoir conditions as well. So this is XPT is more reliable to distinguish or identify the fluid contacts, for which you will build another grid to be used by the reservoir engineer to simulate to simulate the flow. Then we come to the volume assessments. These are we all know this famous equations for calculating STOIP. Okay. We have also other volumes to be calculated. We have the rock bulk volume. We have the net bulk volume. We have pore volume, okay, which is the net volume multiplied by porosity. Then we have the hydrocarbon pore volume for oil. Only we have hydrocarbon pore volume for gas. The STOIP, okay, which is the standard oil in place, and initial gas in place. All these volumes are calculated by the geomodeler. Okay, most of the all the softwares actually in the industry now, like Betray, like RMS, like, they provide you with all these volumes. This is an example for well design. Okay, so you can see this is what we are talking about, the integration of the data. So we have here cross section for the faces. You are trying to capture or follow the good faces where you have a good oil. Okay, you also show the seismic data. You see when you are working on as a geomodeler, you need to be artist with data visualization as well. So and you are visualizing data, okay, in one window, like seismic, like faces, like porosity, like everything, so that it can help you to choose the best location, okay, in terms of structure features, in terms of petrophysical properties, and you design your well to follow the best reservoir properties away from troublesome structures like faults and or fractures. Okay, before I proceed this one, I need to explain something regarding the uncertainty, because I remember that someone asked me about the sorry, the presentation cut that happened earlier to cause all the questions to disappear. It looks like Zoom restarted, when it restarts, it deletes all the messages. So you know that what are the inputs into the static model? Let's count them together. It's let's say SW. Okay, we have the porosity, we have the permeability. What else? We have the net to gross, and also we have the facies. Okay. Okay. Each time, okay, when we run the volume, okay, we are running the volume based on data which represent samples from the field. When you have a field, okay, and you have wells, this is a well, this is another well, this is another well, this is another well, and this is another well. Okay, what do we have is samples. Okay, these wells are just samples from the whole reservoirs. Okay, and we are building a volume and assess the volume based on this data. So this means that we are not calculating the original or the exact volumes in the subsurface. Why? Because we cannot drill well each 1 foot or each 1 meter to calculate to calculate the exact volume. There's no way it can be this can be done. So what we are doing, we are depending, or we are calculating our volumes based on what's called samples, okay, from the reservoir. So these samples are data. Okay, so each time we use this, we are taking this data from different well samples. Okay, so SW, let's say for example porosity. Okay, we have the average porosity from this well is not, might be not the same as average porosity from this well. Okay, so I expect deviation in the data. Okay, and this deviation in the data should be considered when we are calculating the volume. And this is goes and this part we do what's called uncertainty analysis for each reservoir parameters, for porosity, for permeability, for net growth, for SW, and run probabilistic analysis, okay, to see the impact of each parameter, okay, on the volume. And we end up with a with the probabilistic volume, probabilistic volumes, which is the 1p, 2p, or the probabilistic cases. We call it the probabilistic cases, and 3p. So p, 1p is the proven, okay, which is the volume that we that 90% will be produced, okay. 2p, which is the 50%, which is the 50% probability that the calculated volume will be produced. 3p, it's the less case, or let's say the case that less 90% that this volume will not be produced. So we are taking consideration all these parameters, to for uncertainty analysis, to end up with three probabilistic volumes. One volume for 1p, which is the proven. We have the proven probable, and we have a proven, probable, and possible. That's why you have a 1p, which stands for proven, which is the proved, which is I'm sure that it's there and I can produce. 2p is the proven probable, okay, it's 50%, okay, to be produced. 3p, it's 10% to be produced, or 90% that it will not be produced. So it stands for proven, probable, and possible. So I hope this will be understood. Oh, but by the way, the uncertainty analysis, it's a big part of RCM. And it's a very long process, and it's using geostatistical and it uses geostatistical processes. So it needs a geologist or geomodeler with good knowledge of geostatistics. So to calculate the three cases of the volumes by considering the uncertainty of each reservoir parameters, even seismic structure and faults are considered into this into the uncertainty of the volumes. Okay, so now I will talk about the final part of our session today, which is the iteration process between static and dynamic. This iteration process, it's like a repetition. Okay, so the geomodeler, when he finish building the static model, and he's happy with all the inputs and the outputs that he ended up with, he pass the static model to reservoir. Let's say that we are in this phase of static model. When he finishes, he provide the static model to the reservoir engineer to do scale up. What we said about is that it's transferring the fine grid into a coarse grid. Then after that, the reservoir engineer take the dynamic data from pressure to production to relative permeability, and put it into the dynamic model and run simulation. Okay, and after that, he check the history match. So history match, when it comes to history match, we have history match for for quantity of oil. We have history match for quantity of for pressure. We have history match also for gas oil ratio and for water cut. Let's say that we have a production data for oil, for quantity of oil. Okay, this is the quantity of oil. Okay, this is the quantity of oil. Okay, and this is time. Okay, let's say that the field has been producing since 2000. Okay, to up to 2020. Okay, and we have a cumulative production goes through time like this. Okay, at 22, this is the actual. Okay, this is the actual. This is what the field gave us through this time, through the last 20 years. Okay, if the simulation, okay, predicted the history match that respect this one, let's say that a history match, the predicted history match that the dynamic or the simulation predicted goes something like this. Okay, you don't expect it to be exactly the same, but at least to be the same trend. Okay, then at this point the reservoir and the geologist, okay, they can agree that the static model is representative, okay, for the reservoir and can be used further, okay, to field development project and to forecast and to continue drilling. But in case the history match was not like this, let's assume that we run the simulation and the reservoir engineer ended up with something like this, which is much lower in terms of quantity of oil compared to the actual. Okay, at this point, what will happen? The static model will be sent back to the geomodeler to work on the to work on the problem, because this problem actually it's not a problem, it's uncertainty. So this means there is some reservoir parameters that need to be checked, and this is not done by the geomodeler alone. This can be done with support from the reservoir engineer and the petrophysicist as well. Okay, so it's three. The three person. These three expertise work on solving this problem. Petrophysicist is involved when the problem is associated with porosity or permeability, or the geologist if this problem is associated with the fault location, or the presence of fractures, or the absence or the existence of strange facies. So this iteration process keeps going until the history match is perfect. Then as we said, the static model is considered to be reliable and to be used for forecast and to locate the future wells that will produce more oil in the future. Okay, for me, it's the end of this is the end of today's session. So let's come to the questions. So let me go back to the can reservoir engineer do static model? Actually, it's not easy, because static model is geological domain. You cannot use it's reservoir engineers spent 5 years studying the dynamic properties, okay, the pressure and production. So he's mainly concerned in the fluids. Yes, in college they give courses about geology, but it's not, but just for knowledge, it's not for practice. But geologist is the one who practice geology with some background in the reservoir engineer as well. But for a static model, it's better to be carried out by by a geologist, unless you are interested in static model. You need to practice. You need to practice or get more exercises in static. Not in static model, in geology, because geomodeler is multidisciplinary man. You need to be familiar with the sedimentology, you need to be familiar with the petrophysics, you need to be familiar with structure geology. All this take years to understand, because by practicing only you can accomplish good work, not only by reading articles or books. So for me, I think static model is for, or geologist is the best one for static model. Dynamic model simulation, of course, it's for reservoir engineer. Geologists cannot run simulations because it has something to do with the dynamic parameters, especially pressure and fluids. What is the tolerance of volume between static and dynamic? Do you mean the consistency? If you are meaning the consistency, just a minute, please. Sorry, if you are talking about the consistency, actually there should be a consistency between static and dynamic volumes. Otherwise, there will be an issue with the water saturation, because uh, uh, sometimes they have reservoir engineers, they calculate water saturation using different methods. They don't depend on water saturation by using well logs or capillary pressure, especially reservoirs with especially with reservoir with high aquifer energy. So expect in this case some inconsistency in terms of volumes, but both of them should work on fixing this issue, because you cannot go ahead with the simulation as long as you have difference in or inconsistency in volumes between static and dynamic. Okay, tell us about the common pitfalls during the petrophysics integration with the sedimentary model. Actually, sorry, I didn't have enough time, because 3 hours we didn't have much time talking about rock types, but maybe in the future we can have uh, sessions about rock types. So rock types is the challenge work for petrophysicist. It's the work where he is trying to integrate facies and reservoir properties in one rock type. So this means that you have what's the what petrophysicists try to do with the rock type. Petrophysicists try to have to create a rock, okay, rock unit. Okay, this is a rock unit that has, okay, a unique facies. Okay, a unique facies. Let's say that we have a unique facies, like let's say a grain stone, okay, for carbonate or grain stone or pack stone facies. Okay, it should have this unique facies, okay, should have a unique petrophysical properties, like a unique porosity or average porosity, or unique range of porosity, unique range or average permeability. Same for water saturation, and same for water saturation, same for pore volume, okay, and average pore volume, and also average PC curve, as well as average relative permeability. This is the most challenging part for petrophysicists to do, to generate rock types, okay, that combine all reservoir properties within certain within within inside one certain unit. Okay, so this is, we call it rock type 1. Okay, rock type 1. Rock type 2, it has another certain reservoir properties, range or average. Believe me, it's not easy task in carbonate. In sandstone it can be easy, but in carbonate, especially very heterogeneous carbonate, I work, and I'm still working on some carbonate reservoir, which, believe me, rock type is still a nightmare for to accomplish, but it's very interesting part. So this is how you can. So this is one of the pitfalls to I don't want to say it's pitfall. You can say that it's a challenge. Okay, it's a challenge to accomplish this because you cannot provide the geomodeler reservoir properties to distribute it without a guidance. You need either facies or rock types, and in most of the cases in carbonate you need rock types, not facies, because carbonate facies, you might have a Pakistan facies with good and bad reservoir, with good and poor reservoir properties. So you need the rock type to represent all this. Okay. Yes. Okay. Discrete data. Discrete data, as I said, if you remember, we talked about discrete data, which is not which has not continuity. Okay. Like logging data. Logging data is why it's continuous, because it as the tool goes down along the borehole. So this is my tool. So this tool keeps this tool, as it keeps going down. Okay, it's continuous. It provides us with continuous data. Okay, so it's each half of it record number. It gives us number, so it gives us a logs like this. This is continuous data. Okay, but for core, okay, when you take a core, okay, core is not continuous data, because sometimes you are taking a core from separate intervals. So even the faces inside is not continuous. So you have the okay. Let me take some shapes. Okay, it's better. So you have you have you have faces. Okay, let's call it faces 1. Okay, which extend from, let's say, from 100 feet, let's say, to 105. Okay, then we have another different faces. Okay, it's not the same faces, it's different faces. Okay, extend from 105 to extend from 105 to, let's say, 110. Okay, then it moves again. Sometimes you have a gap. You didn't have even faces due to the broken rock samples or damage. So that's why it's not because there's no continuous recording. Okay, so you have a faces 1. If faces 1 is continuing along the borehole from top to bottom, you can say it's continuous data, but this is not possible. You have a different faces, so you can consider it as discrete data. Another example for discrete data is fracture data. The faults is discrete data. Fractures are also discrete data. The barriers is discrete data as well. It's not continuous. Only when logs, you can say that only when logs is can be considered as continuous data. this simple curve. Yes, it's simple. Yeah, you're right. For only homogeneous rock, yes. In reality, it's different from this, of course. Yes, in carbonate, sometimes the same phases. Okay, some phases, the same phases, you find different behavior for the same phases. They can you are taking the same phases, okay, from different different depths. When you take samples for scale data and you see the PC curve, you see different behavior. Some of them is good, indicate good reservoir, and others they are not. They are poor reservoir. But it's the same phases. Of course, it's not easy. I'm just showing the simple case, but believe me, it's another challenge. It's not that easy. Can we predict sand prediction based on reservoir? It can be predicted. Okay, actually, okay, let me think about it. Can we predict sand prediction? You are talking about here this. You are talking about this the net pay in the new wells, or it can be predicted. I'm not sure if I understand your question exactly. I'm confused if you are talking about in terms of production or you are talking about of net pay. The relation between depth and pressure should be in TVD or should be in TVD. Okay, okay. It's up to you. If it's a vertical well, I don't think that there will be so much difference between TVD and MD. But if it's in horizontal well, it's it's preferred to use TVD. Yes. Okay. Could you please tell us about your experience? Okay. Such as the major largest sand reservoir will be built into the static model and to the dynamic model. But what if we find minor smallest recovery factor? Now, okay, you are talking about small scale reservoirs. If we find one structure, okay, had major and minor reservoir. You mean one structure has major and minor reservoir together? Okay, in case okay, you will go through the same workflow if you have either. Okay, actually, what controls what controls the development of any of any reservoir is the volume. Is it economical? Okay, the structure can be large, but sometimes it's large, but it doesn't have economical volume to be extracted. So what's the use from paying money to exploit this reservoir? So but since it's economical, this means that there is a business. So you can go through the same process or the same workflow of RCM. Yes, okay, but if we find so if there's a good quantity of hydrocarbon to be exploited, then you can go through the same workflow. If there is no, then why you should even think about it? Huh? Proxy models. No, do you know about the proxy model for the design of experimental estimate recovery factor? I think this is the reservoir part. No, unfortunately, I heard about it, but it's made a reservoir part. I'm not sure if I don't think that I can answer this part. Do you know about the proxy model or DOE design of experiment to estimate the recovery factor in percent for the minor reservoirs that were not modeled in Eclipse? If yes, can you explain? No, sorry. I let this part for one of the attendees who is a reservoir engineer. Maybe he can answer this part. For me, I'm geologist, so I cannot. Sorry. Okay, how we can do faces modeling. Okay, as I have shown you earlier in the slide, let me go back to the slide. Okay, this is faces. Okay, faces modeling. When you want to do faces modeling, first you need the data. Okay, so you take the core the faces from the sedimentologist. Sedimentologist do core description. Okay, he describe the core. Um, to plot make a plot for core logging that shows the faces distribution of faces from bottom to top. Then he provide what he does. He provide this faces as a digital data. Okay, for the geomodeler to input into the static model for each well. After that, we go to scale up process. Okay, scale up process enable us to input these faces, okay, into the cells. Okay, so let's say that you have, for example, we have the let's say that we have here okay, we have let me okay, this is faces. Okay, and this is another one. This is another one. Upscale process enable us to do what? To uh, back. Okay, this is faces 2. This is faces 3. Okay, this is the raw data. This is my raw data along the well. This is my well, and this is my face. This is my face. Now I do a scale up process. Scale up process, what do the software do is that will change these faces into the cells that I have. I have a cells, okay, like this. Sorry again, drawing is not that good, but I'm trying to make things clearer. Okay, so what it does, it will come to to this faces, okay, measure the thickness, then come to this cell and fill it with F1. Okay, now second cell, it's still adjacent to the raw data of faces F1. Okay, so it gives F1. After that, in this cell, what it does, it comes to see the software see that there's a boundary between the faces 1 and faces 2. So which faces to put? So in the upscale process, you can define the way of upscaling. Okay, based on arithmetic value, the maximum value, or the minimum value, or the most of. Okay, most of approach. Most of approach. When you choose most of approach, the software will it will see how much of this faces is how much how much this faces is occupying relative to the cell beside it. Okay, and how much the space the second phase is occupying. Let's say that from here to here, okay, it's about 70%. Okay, 70% of of phases F1 occupying this cell, and 30% will be occupied by what? By the second phases. This phases. So what does the software will do? It will consider that this cell is for phases one, since it's representing 70%, the cell representing 70% of the space of F1. So it will consider it as F1. Then after that, okay, it will go to the next cell. It's in F2. It will give it F2, and so on. After that, you will distribute the faces using stochastic algorithms. Okay, like indicator. There are two famous algorithms, which is first one is truncated Gaussian simulation and indicator Gaussian simulation. The most famous stochastic algorithms that's used for distributing faces in 3D. So I hope this answered your question. So any other questions? What if we Dave logs only? You mean use logs only? Okay, you mean in case you don't have faces? Okay, all right. In case you have no faces, and this is not favorite because faces need to be you need to be applied so that you can build. Uh, it's essential for building a proper property model. Then you will be using you will start doing what we call it petrophysical group using cutoff values. Because what's important about phases? Phases is that we needed to distinguish good reservoir phases from poor reservoir phases. We know that poor reservoir phases like shale, it's not contributing to production because they have no good permeability. This is what we need about phases. If there's no phases, then we will have to follow another approach. Okay, using cutoff result cutoff and apply it on other reservoir properties like porosity to distinguish where we have good reservoir good reservoir good reservoir rock units and which have good reservoir properties, and where are the poor reservoir property or poor reservoir phases which have poor reservoir property, because this is very important for the simulation. So this is in case you don't have in this case you need to have phases, because you need to know where are the poor reservoir properties located and good reservoir property located, because it will help a lot for simulation and to predict the flow behavior. Okay, for okay, for variogram. Okay, for all right, for okay, for variogram. Variogram, it's spatial analysis. Variogram is generally spatial analysis. It's used to predict the distribution of the phases between the wells. Okay, so let's say that you have okay. Let's say that you have a well here, okay, and you have a well here, okay. You have a phases. You have phases one. You at some at certain layer, you have a phases one here, okay, okay, and you have a phases two here, okay. You don't have phases one, okay. You have phases two at the same depth. Let's so what does that mean? This means that phases, there's a change in the distribution of phases from phases one to phases two. Let's say that there's about 1 kilometer or 2 kilometers from this well to this well. Okay, this is 1 kilometer. Okay, this means that phases one just somehow in some part between two wells disappeared. Variogram help us, okay, to map, okay, or model, okay, the distribution of phases one, considering the reality that it's not extending beyond phases two. So the variogram the variogram will consider the direction or the dimension in x and y direction, okay, and you put it into the stochastic process and run several cases, okay, and each time you expect the simulation will give you since it's simulation, it will give you the the boundary or the limit between phases one or phases two. Maybe sometimes it gives you here, sometimes it gives it here, sometimes it gives it here. It's based on what? It's based on the experimental values. This is called the experimental variogram, based on the major and the minor or the x and y values that you input. Then you compare that. Then how you can make sure which one is best is by comparing with the input data that you have and see the percentage, are they identical or no. Okay, to predict the value of permeability if core is not provided. Well, actually, yes, I told you it can be done, but as I told you, in carbonate, I'm talking about carbonate reservoirs, it's not easy task. Several papers, I read several papers talking about the efforts to predict permeability from well logs, but some cases was successful. Okay, especially in, uh, in uh, in carbonate reservoirs where you have some less heterogeneity compared to complicated reservoirs, but it's not always it's not always applicable to other reservoirs. Some of these methods were empirical, okay, using different equations like Timor and Texar and others. There is also you can use multivariate analysis by using integration of several logs, but also this is not very successful in carbonate. So I think core data is mandatory for permeability prediction in case of carbonate. Okay, any more questions? Okay, it seems that we no longer, okay, can be, of course, yes, it's not only about faces modeling only. The more data you have, the less uncertainty you have in any reservoir parameter. So if you want to do a good faces modeling, you need to have enough or enough samples from the reservoir to represent faces of the reservoir. If you so let's say that if you have a large feed with the 3-4 wells with the core data and faces, of course there will be high uncertainty for the distribution of these faces. But let's say that you have the 10 or 15 core data from these 15 wells. Make sure that uncertainty will be reduced, and your faces model will be more representative for the reservoir faces. So always more data equal less uncertainty. You're welcome. You're welcome. Okay. I think it's done for today. I think that no more questions.
Yes, Mr. Tajuddin, thank you all for your effort. I think that it was very, very interesting workshop for us. And also, I think that all the participants enjoyed the discussion with you, especially regarding your great experience regarding the static modeling and rock typing and so on. So thank you for your time.
Thank you. Thank you very much. Thank you. Thank you, everybody.
Thank you. And also thank you for all the participants that attended our session until the end. Also, I wanted to remind you that if you wanted to have a certificate for attendance for that workshop, you should fill into the form that its link was sent into the Zoom chat. Also, if you wanted to enroll into our upcoming course regarding reservoir characterization using core data, also you can register and view the course content from the links that will be sent into the Zoom chat. Thanks everyone, and hope to see you into the next event. Thank you.
Okay. Thank you. Thank you.
Thank you.